So now that you know how to calculate the expected value and standard deviation of a random variable, we're going to move forward by doing a few problems that are a little bit more complicated than the ones I showed you previously. These problems deal with dependent events, and so the probabilities are a little bit more complicated. Let's start by remembering the formula for the expected value of a random variable, or the mean of a random variable. We're going to take each possible outcome, the numerical value of that outcome, and times it by its probability of occurring, and then sum up all of those terms. For the standard deviation, that's calculated through the variance by taking the square root of the variance. And the variance is calculated as the difference between each outcome and the expected value. We square it and times it by its probability of occurring. And then we sum up all of those terms. So we're going to do that for the next few problems. Let's start by looking at this problem in which we play a doubleheader of baseball and we want to predict how many games we're going to win. Based on past experience of playing this opponent, we came up with some probabilities. So for the first game, your probability of winning is 0.7. And then the probability of winning the second game is dependent upon how you do in the first game. If you win the first game, the probability you win the second is 0.6. If you lose the first game, the probability you win the second is 0.5. So these are dependent events, and we need to take that into consideration when we're calculating the expected number of games won and the standard deviation. So because these are dependent events, we can display these probabilities using a decision tree. This first branch represents the probabilities of winning and losing the first game, and you can see that they sum up to 1 because that's the entire sample space. You either win or lose that first game. The second game is represented by these two branches here, and they, again, probabilities depend upon whether or not you win or lose that first game. So if you win that first game, the probability you win the second is 0.6, and that's given to us in the problem. We can deduce from that then the probability that we lose is 0.4 because these are our only two options and they have to sum up to 1. The same thing for the bottom two branches. The problem tells us that if we lose the first game, the probability that we win the second is 0.5. That information is given to us, and then we can deduce from that the probability that we would lose. It has to be 0.5 because these have to sum up to 1. These last set of 4 probabilities that I've calculated then, I calculated using the multiplication rule. So the way we calculate the probability of 2 wins is just multiplying those two probabilities together. So 0.7 times 0.6 is going to give us 0.42. The same thing is calculated for these other probabilities. Lose is just 0.3 times 0.5, which gives us a probability of 0.15. This last column, its probabilities, are what we're interested in because these 4 outcomes are the outcomes we're interested in determining the number of games won, or the expected number of games won. So the problem asks us, what is the expected number of games won? So you could think of the number of games won as a random variable with 3 possible outcomes. You could win no games. That means you lose both the first and the second game. You could win 1 game, either the first game or the second game. But if you win 2 games, that means you've won 2 games. The number of games won is 2, and that is the last outcome. So then we're going to use these probabilities to calculate the probability of each of these outcomes. So the probability that we win 0 games is the same as the probability of losing 2 games in a row, so 0.15. The outcome of winning 2 games means we win the first and the second, so that probability is the same. The last one, outcome of winning 1 game, means that we have 2 ways that we can win 1 game. We can either win the first and lose the second, or we could lose the first and win the second. And those are disjoint events because there can't occur at the same time. So we can just simply add those up. You can see these three probabilities add up to 1. That's our entire sample space. And so this probability assignment is valid. So now that we have the probability assignment, calculating the expected number of games won is pretty straightforward. You take each outcome, each numerical outcome, 0, 1, and 2, and times it by its probability that it occurs. So 0's probability of occurrence is 0.15, 1's probability of occurrence is 0.43, and 2's probability of occurrence is 0.42. So the expected value is 1.27. Now we know we're never going to win 1.27 games. We're either going to win 0, 1, or 2 games in one meeting of a doubleheader. What this number represents is the long run average. So for example, if we were to play 1,000,000 doubleheaders, of those doubleheaders, we'd expect on average to win 1.27 games. So this is just a long run expectation. The next thing we want to figure out then is the standard deviation of the number of games won. That is, sometimes we're going to win less than 1.27 and sometimes we're going to win more than 1.27. So how much variation do we expect? We can calculate that standard deviation using the expectation. So again, we're going to square root our term. So that's the last thing we're going to do. What we do first is we take each observation or each outcome, which is 0, 1, and 2. We subtract from that the expected value, and then we square that difference and then times it by the probability that it occurs. So again, winning twice has a probability of 0.42. And so this is the standard deviation that we'd expect. When we calculate this out, we get 0.705. So what does this number mean? This number, again, is just a measure of spread of the outcomes. Our outcomes are 0, 1, and 2. And so this is just capturing that spread in the data. The expectation is the center where we think the most of the outcomes are going to be. And then this second term, the standard deviation, calculates the spread of the data. So as I mentioned in the previous video, once you have a mean and a standard deviation, you can apply the normal model just like we did in the previous section. So we can use the 68, 95, 99.7 rule. We can use the z-tables to find proportions or other probabilities and learn more about our expectations. So let's go over a problem now that makes a little bit more sense why we would apply the normal model to. In this problem, what we're trying to find is the company's expected profit. So you can think of profit as a random variable, and the probabilities that it depends upon are whether or not its policyholders suffer injuries, and those injuries may be major injuries or they may be minor injuries. The insurance company actually loses money when someone gets injured because they have to pay them. So the insurance company pays them $12,000 if the policyholder suffers a major injury. But if that person suffers a minor injury, they pay $2,500. If they don't suffer an injury, they don't pay them anything. The policy costs $150, so for everyone who signs up, the insurance company receives $150. So there are three possible outcomes. The policyholder is not injured, the policyholder is injured majorly, or the policyholder suffers a minor injury. Those are disjoint events because they cannot occur at the same time. What we need next then is probabilities for each of these outcomes, and the problem gives us as well. In all likelihood, where these numbers probably come from is the company's past policyholders. So what they've found in the past is that 1 in every 1,984 policyholders, someone suffered a major injury, and that 1 in every 469, someone suffered a minor injury. Now for this problem, we said there are 3 outcomes, and these are the probabilities for each of these outcomes. You can calculate major injuries as 1 over 1,984. The probability of suffering those minor injuries is just 1 over 469. So that's how I got these 2 numbers. The top number then is just 1 minus these 2 numbers because these 3 numbers have to sum up to 1. So as you can see, the probability that no one suffers an injury is really, really high. The probability that someone suffers a minor injury or even a major injury is really low. Major injuries are even smaller than minor injuries, and that's what we would expect. The last thing you may be asking yourself about is how I got these numbers for profit. So these numbers for profit are based on whether or not the policyholder injures themselves. So as we said before, they make $150 on each policyholder regardless of injury. So if there's no injury, they make $150 and that's it. They don't have to pay them anything. If the policyholder has a major injury, they lose $1,200 and they were going to make $150, so we subtract 12,000 from 150 and we're left with a negative profit, negative 11,850. Same thing for those who suffer a minor injury. The policyholder receives $2,500 or the insurance company pays out $2,500, and so overall they will lose negative 2,350. So that's the hard part of this problem, right? Setting up the probabilities for each of the 3 possible outcomes and then determining the profit for the 3 outcomes. Once we have all of these numbers, the rest is simple calculation to get the expected profit. So here we're looking at the expected value of the profit of one policyholder, and so we just multiply each outcome by the probability that it occurs, and that will give us an expected profit of $138.62. We can also calculate a standard deviation, which I'm not going to go through again in this video, but I'm going to show you the value here is $292.88. So that's a measure of how much spread we would expect to see in the profit of one policyholder. So now that we have the mean and the standard deviation of one policyholder, we can ask more complicated questions. We could say, what's the expected profit if we were to sell 10,000 or 10 million policies? We could even try to figure out the likelihood of making more than $1 million or $2 million. And so we can start to use the normal model and make linear combinations of these random variables. But before we get to those more complicated problems, the first thing we need to do is we need to talk about some of the properties of expected values and the variance measure or standard deviation measure. We're going to talk about those properties of random variables next, and then we're going to move on to the normal model.